This video is a guide to calculating the gravitational potential store of an object when you're given the object's mass and its change in height. It assumes you've already watched a video on the gravitational potential store of an object when you have its weight and its height. So let's start by looking at the equation we had last time. We have delta Eg. The triangle symbol is a delta and it means a change in. E is energy and G is gravitational potential. So we have the change in the gravitational potential store is equal to W times delta H, where W is weight, delta again means change in, and H means height. So we have that the change in gravitational potential energy store is equal to the weight times the change in height. Remembering that energy is always measured in joules, weight is always measured in newtons, and height will be measured in meters. Now there's another equation we should know. We should know that the weight of an object is given by its mass times by the gravitational field strength. With this equation, we can substitute into the first. We can replace the W with the M times G, and that gives us a new equation. This equation is that delta Eg, or change in gravitational potential store, is equal to the mass times by the gravitational field strength times by the change in height. Now on Earth, the gravitational field strength will be considered 9.8 newtons per kilogram. So for instance, on the Earth, I have a mass of 65 kilograms. However, my weight on Earth is 637 newtons. If I were to go to the Moon, where the gravitational field strength is lower, it is about 1.6 newtons per kilogram, my mass will still be 65 kilograms. However, my weight will be 104 newtons. I will have less weight on the Moon. Now, generally when we're dealing with these equations, we will be considering objects on Earth, and so we will be using G as 9.8 newtons per kilogram. So we must remember again that energy is measured in joules, mass is measured in kilograms, the gravitational field strength is newtons per kilogram, and height is measured in meters. So let's look at a couple of worked examples. A weightlifter lifts a 50 kilogram mass a distance of 2 meters from the ground. Now we're going to assume that he's on the Earth. So we have delta Eg is equal to M times G times delta H. Now we have M, which we know because we have kilograms next to the 50. That's the mass. So we replace the M with 50. We know that the change in height is 2. And we also know that the gravitational field strength is 9.8. So we replace the M with 50, the G with 9.8, and the delta H with 2. This gives us 50 times 9.8 times 2. And so therefore, the change in the gravitational potential store is 980 joules. Next, a pulley is used to lift a 12-ton mass 0.8 meters above the ground. Calculate the change in energy in the gravitational potential store. In this case, we have 12 tons. This is not kilograms, and so we cannot use that number. We need to make a conversion. We know that 1 ton is equal to 1 megagram, which is the same as 1,000 kilograms. So if 1 ton is 1,000 kilograms, that means 12 tons must be 12,000 kilograms. Once we have that number, we can write down our equation again. We can replace the M with 12,000, the G with 9.8, and the delta H with 0.8 meters. This gives us that the change in the gravitational potential store is 94,080 joules. However, since we've only been given 2 significant figures in our question, we will give 2 significant figures in our answer. That gives us 94 kilojoules.